one is first learning NMR spectroscopy, you often discover that of the carbons that have hydrogens on them, the methyl, the methylene, and the methine, it is the methylene group, the CH2, that often causes quite a bit of complication in an NMR spectrum. There are ways of dealing with it, and in this and in subsequent videos, I want to talk a little bit about how we deal with the complications that methylene groups give us. They can be quite complex in cyclic molecules, chiral molecules. Today, we're going to look at a somewhat simpler example that methylene groups in particular are quite susceptible to: signal overlap. The fact that their chemical shifts are so close together that they're going to appear clumped together in an NMR spectrum. And some of the ways we can go through our data to nail down that that is exactly what's going on and how to explain it. And as I often do, a PDF of the spectra that you're going to see is available in the comment section on the YouTube video. Feel free to download those and have them in front of you. Play along if you wish. Let's take a look at this. Now, certainly, methylene groups can look just like the textbooks tell us they ought to look. In a simple molecule like this one, methyl ethyl ketone, there's the methylene group. Focusing in on it, it is just a gorgeous quartet at exactly the chemical shift we would expect. In fact, if we just take a look at that thing for a moment, it just warms our hearts to take a look at that and just see how beautiful it is. And even in larger molecules, the somewhat larger here butyl butyrate, 5 methylene groups in this thing, and a number of them are exactly what a textbook would tell us we ought to see. For example, this one over here, CH2 group, a methylene, right next to the oxygen of the ester. There it is, right over 4 ppm. It has 2 neighboring protons. It is a glorious textbook triplet. Beautiful. We look at this one over here next to the carbonyl carbon. It's just over 2 ppm, like we would expect it to be. It has 2 neighbors. It too is a glorious triplet. Beautiful. Even over here, we see this group. Now, here is this methylene group in a, not in the middle of things. On one side, it has a CH2 group. On the other side, there's a methyl group. It has 5 neighboring protons. And sure enough, it is a glorious sextet. Beautiful set of peaks here. Exactly what we would expect from 5 neighboring protons, and the coupling constants to all of these protons being nearly equal. But as we look at this spectrum, sure enough, we come to this group in the proton spectrum. It integrates to 4, and with knowing the structure of butyl butyrate, we're pretty certain this is 2 overlapped methylene groups. And indeed it is. It does integrate. The fact that it integrates to 4 is a strong indication that it is 2 methylene groups overlapped. And sure, we know what the structure of the molecule is. But I want to walk through, how do you actually prove it beyond a shadow of a doubt, particularly in a situation where you don't know exactly what the molecule is. You don't have the structure sitting there right on the spectra. Your best friends for untangling methylene groups, when in a lot of different situations, including when they are overlapped with each other, is the combination of depth spectra, particularly depth 135, to confirm a carbon is a methylene group, and then heteronuclear correlation, such as an HSQC spectrum, that will tell you exactly which carbons are attached to which protons. Let's take a look at how that works for this particular sample. First, the depth 135 clearly confirms that there are a lot of CH2 groups in here, and in fact there are all 5 of them. Now we look at the HSQC, and I want to focus in right here on the area where the overlap is occurring. And sure enough, what do you notice but that there are 2 carbons correlating in this region. And in fact, it's not these two carbons that look like they're so close together. It's actually a carbon, the two carbons are over 10 ppm in the carbon spectrum apart from each other. But in the proton spectrum, they are virtually overlaid on top of each other. And so if you have a proton signal like we do here that has multiple carbons that correlate to that position, such as the two that correlate here, that is absolute convincing proof that this complicated signal that integrates, to 4, and unless, let's face it, unless you're running the spectrum of methane, which is kind of a boring spectrum to run, you don't have 4 protons on one carbon. So this must be a set of overlapped signals. And indeed, it is 2 methylene groups. The depth 135 shows that these 2 carbons are indeed CH2 groups overlapped, giving us a complicated looking signal. It's not a textbook doublet or triplet or anything else. That is integrating to 4, 2 methylene groups overlapped. HSQC combined with depth 135 make that abundantly clear. And if we look at this particular signal, it does not have the textbook look of any classic doublet, triplet, quartet. And in fact, you can, if just looking at it carefully, you could tell the line widths of part of this are not the same. Dead giveaway that this is more than one proton, that are unequivalent protons that just happen to have nearly the same chemical shift and are appearing over the top of each other in our proton spectrum. For those of you playing along at the home game, you will also notice, if you look at these, that the methyl groups of butyl butyrate are actually pretty badly overlapped as well. You see it in the proton spectrum here, where it does integrate to 6. Look at it carefully. In theory, these 2 methyl groups are different, should have different chemical shifts. The molecule is not symmetric, and indeed they do, but they are almost the same. Look at this thing. This is not a classic textbook doublet or triplet. This is 2 triplets almost overlapped each other. If you look at it carefully, there's one triplet here, 1, 2, 3, and the classic 1 to 2 to 1 ratio. Here's the other, 1, 2, 3, classic 1 to 2 to 1 ratio. It's actually a lovely, lovely pattern. Just makes me feel so good to think about. And sure enough, you also see it in the carbon spectra. We focus in on the methyl groups. The depth 135 told us these are methyls. It looks like one peak, but if you zoom in very carefully, oh, there it is. They are 2 peaks. Again, almost perfectly overlapped, but not quite. We can see the difference. Overlapping signals, particularly overlapping methylene groups, quite common in large molecules. They reveal themselves in the proton spectra by integrating to unusually large numbers, 4, 6, things like that. How do you nail it down to prove it, especially if you have a spectrum that's going to become, part of the data for a publication? Your best friends are the depth spectra, particularly depth 135, and heteronuclear correlation, HSQC. If you have a signal that you suspect is overlapped, the HSQC will show you which carbons are bearing protons that add together to give this complex overlapped signal in a proton spectra. It's a very nice experiment that allows you to see when overlap occurs very nicely. So I hope this helps, and we'll talk to you later.